Okay, this is going to be a lecture on quadratics. And perhaps the most important calculation for beginning students of algebra. And it certainly has significance all the way through calculus and beyond. So let's have some conceptual discussions today. You've been working with some of the mechanics of quadratics, a fancy word for rectangles, for a week now. Perhaps we can dive in a little deeper as to what's going on and how we might use quadratics and apply them to a simple situation, which I'll do at the end of the video. All right, but let's have a good discussion here about what you're doing and why, and talk about the origins of the discipline a little bit. All right, so can we see everything? Yes, we can. All right, so here's, some table values. -3 times -3, 9, -2 times -2, 4, -1 times -1, 1, 0 times 0, 0, 1 times 1, 1, 2 times 2, 4, 3 times 3, 9. And I'm using bar graphs to kind of show those amounts, those y values. So you want to know a y value, it's the vertical strip as measured from the x-axis. And these y values are being determined by squaring a dimension. And I think we can see that the areas are decreasing to 0 and then are increasing on the right-hand side of this particular algorithm. Fancy name for a calculation. Now we can talk about how things are changing by talking about rise over run, which is really the change in y, triangle y, change in y over change in x. And as the dimension changes by 1 unit, looks like it's gone down 5. And we can do the rise over run to get a little feeling for what is called the average rate of change. And I'll just use a triangle. Average rate of change from that dimension to that dimension, or from this one to this one, is down 5 over 1. Whereas the average rate of change on the next one is down 3, and then the next one is down 1. And so the change is changing. Okay. And on the other side, we have symmetry. On this side, we're going up by 5, and we're going up by 1. And so as we move to the right, that's how you read graphs. You follow the graph from left to right, decreasing, then increasing, and at different rates. Well, what if we wanted to get a feeling for how it was changing at a given moment? Well, then we got to zero in a little bit. That average rate, that distance and dimension has to get smaller. Right? So we go from maybe 2 to 2.001. And still get a feeling for, well, how's this calculation changing it over that interval? And it turns out there's some nice patterns for squaring. If I square 2.001, I get 4.004001. If I had done 2.00001, 5 decimal places, I would have had 4.12345. 1, 2, 3, 4, 5. And there's still a little bit of a pattern there. And if I look at that, if I want to see a pattern, I got to do other numbers. So I'm going to do 3 at this point, and then I'll expand that out. 5 decimal places gets me 0.00601. And this number here could have been expressed as 9.00006 plus 0.0000000000, and that should be 01. And if I put those numbers together, I get that number. Now NASA, I heard this, uses 8 decimal place accuracy to send people out into space. So they would ignore this. And they would say that this number is changing. This change is 0.00006 divided by the change in x, which is 5 decimals. 1, 2, 3, 4, 5. Turns out that's 6 to 1. And if we did the same thing here, we'll use this one. This one is 5 decimals, 0.00004, and divided by 0.00001. Well, that's 4 to 1. Which happens to be twice the x value you started with, twice the x value you started with. Well, I'm sure somebody didn't see that immediately. I don't know, it could have been decades of mathematicians working with things until somebody went, I see a pattern. So you're just sitting in this chair and not doing much math yet, just pointing things out, so it won't take you decades to see it. All right, so what went on here? Well, let's look at a square. Let's look at a 2 by 2. Let's look at any generic square. It's got area. If I want to make the area bigger, I could simply put a little layer on it of length and width, which is 2 sides of a square, which has something to do with doubling this too. Now I'll do the numerics for it. So let's say we go up by 0.001. Let's just go up by 0.01. Right? Then this thing has 3 parts to it. In order to maintain the square shape, then that dimension in that direction has to go up by 0.01. And this one has to go by 0.01. And this is 2 units long, and this is 2. And this is 0.01 squared, which is 0.0001, and we're going to ignore that. So what's the new area? Well, the change in area used to be 4, but it has increased by 0.02 here and by 0.02 here, which is an increase of 0.04, and 0.01 was the increase in diameter. And we're getting a little feel for how this thing's changing over a small interval. Still the same concept as in your pre-algebra, y2 minus y1 over x2 minus x1. I'm just doing it over a small interval. And I happen to know the patterns because I've been teaching for 45 years and I spotted them. And that's a pattern, geometric pattern. All right, so what are some of the things you're going to be working with and need to know? Well, one thing is parabola, cup-shaped cup. If we wanted to hit a height of 9, there's a positive side and a negative side. So when you solve this, you need to say plus minus the square root of 9, which is plus or minus 3. I have students who go the whole semester and can't remember to put plus minus in front. I hope you're not one of them. But you won't be alone. So that's the good news. Bad news is you didn't learn to put the plus minus there. So I'm telling you early in the semester, so you got the whole semester, and by the end of it, you might remember it, and then next year, you might remember it again. Hazelnut coffee, yummy. All right, so where did this calculation come from? Rectangles, right? Length times width. All right, and when the first archaeological dig found somebody saying area equals length times width. But that's for generic rectangles. The square is simply the side of the square. It's the side of the 4-sided figure squared. That's the language that we're dealing with here. And it turns out you've been practicing x plus 2 times x plus 8 and getting area statements of x squared plus 10x plus 16. Why? You got to start somewhere. Right? We're starting at the beginning here. You're looking at, well, what is x plus 2 times x plus 8? And in class, we might have started with 1 plus 2 times 3 plus 4. Seeing the 1, 3, 1 times 3 plus 1 times 4 plus 2 times 3 plus 2 times 4. That whole process, right? So you can trust for all numbers that x plus 2 times x plus 8 is x squared plus 10x plus 16. All right, so that's just mechanical practice. So let's extend that to the next consideration. Let's see, do I have everything captured? Yes, I do. All right, so we've got this x squared plus 10x plus 16. Well, what if we set it to 0? What if we had an initial calculation? We said, well, what makes this area equal 0? Well, it would be logical to have the skills, x plus 8 times x plus 2, to develop those skills. They're called factoring skills. You know, we're taking a sum to write it as a product, x plus 2. Well, I guess I got it down here. I don't have to write it again. And so if that equals 0, well, how do you make the area of a rectangle equal 0? You got to get rid of one of the dimensions. You got to either get rid of width, no area. You got a rectangle with that kind of width, and you get rid of the width, there's no area. Same thing with height. Squash it. So what gets rid of the width? Well, let's put a 0 in. 0 plus 8 is 8. That didn't get rid of it. Negative 1 plus 8 is 7. Well, it's getting smaller. Negative 2 plus 8 is 6. Oh, but you know what happens when you put -2 in here? Oh, you got no height. You got no height, you got no area. So that's one of the skills you're practicing. Factoring quadratics, setting them to 0, seeing if you can factor them, and if you can, then you can see the dimensional changes. And you've got an answer to an equation. All right. I'm gonna have to find out what equations are for. But what happens if it's not set to 0? Well, that gives us something like what's written up here, x squared plus 10x plus 5. Okay, well, why can't we solve that using factoring? Well, I can't think of two numbers that multiply out to 5 that add up to 10. That's one of the problems. So what do we do? Well, when we think about equations that we have solved historically to this point, and I'm guessing linear preceded quadratic, and people figured out that, well, you can use 2 inverse operations, -6 divided by 5. No, we've talked about that in class. Why can't you use inverse operations here? Well, one of the operations you'd have to use is square root. The only problem with this is it's not a square. So somebody probably started thinking about that. Like, probably a brilliant thing came into the mind. Like, can I make it a square? Because if I can make it a square, I can use a square root. And I can isolate the x. Wouldn't that be nice? Right? Because, you know, if you look at, for instance, x plus 5 times x plus 5, you get x squared plus 10x plus 25. But you know what? You could also write that as x plus 5 squared. Yeah, so x squared plus 10x plus 25 equals x plus 5 squared. Well, let's say we wanted this to equal 7. That's a problem. 25 minus 7 is 18. I can't think of two numbers that multiply out to 18 and combine to 10. But if I set this to 7, not a problem at all. All I got to do is take the plus minus the square root of 7, move that operation, and then move that over, and I got an answer. Well, wouldn't it be nice if I could make this into a square? So let's consider it still equal to 0. Let's consider this equal to 0, right? And we already know if this equals 0, we get -8, -2 for solutions. Right? We can see that if this is 0. But how can I make it into a square? Well, why isn't this a square? That's longer than this. Well, what if we were to reshape it? Make the smaller side longer and the longer side shorter. Question is by how much? Well, let's even it off and find out. Oh, let's make it 5. X plus 5, x plus 5. And we know what that is. That's x squared plus 10x plus 25. That's pretty darn close to this. I got the first two terms. But 25 has got to be what? 16. Marker. So what have I got now? I've got x plus 5 squared minus 9 equals 0. Therefore, x plus 5 squared equals 9. Therefore, x plus 5 equals plus or minus 3. And therefore, x is equal to -5 plus or minus 3. And -5 plus 3 is -2. -5 minus 3 is -8. Then I just found a way to take non-factorable quadratics, rectangular situations, and I can work with them. And that's called completing the square. Seems like a logical thing to call it. Right? Took a rectangle and changed the dimensions, worked with it. Oh, I remember I have a rule of 4. Might make this a rule of 40. You got to think about this a long time. You got to give it your thought process, and you got to give it consideration, and you got to continue to do that until it makes sense, which means you're tasked with mindfulness. It means if you're listening to your phone right now, give up, just stop the video. No sense trying. You know, if you're on a conversation with a roommate or something and you're looking at this, I suggest you wait for another time to start thinking about these things. I'm being a little harsh here, but you got to learn to be uncomfortable or comfortable being uncomfortable. In other words, math concepts aren't something that just happen. And the further you go up the ladder in this discipline, the harder it's going to get. So here's your chance to start practicing some mindfulness around conceptual mathematics. What's going on and why? Let's continue the video. Got to get this done in 45 minutes. Yep, I don't need to do that. I'll move the camera instead of the desk. Do I have everything? Let's see. Yeah, good enough. So, you know, we're basically learning how to take a quadratic, ax squared plus bx plus c, and write it in this form. It has a usefulness for solving equations and for also picturing the relationship, the numbers. A picture's worth 1,000 words. So something like 2x squared plus 40x minus 7. Right, well, I know how to do this. I've done 200,000 of the minimum. And so I've got minus b over 2a minus 40 divided by 4 minus 10. It's plus, but in this case, minus 10 makes the 0. Right, and so then if I put minus 10 minus 400, I get minus 207. I believe that's correct. Right, now I got the roots. I got the roots, negative 10 plus or minus the square root of 207 divided by 2. Right, I mean, with some practice, you'll see that yourselves. But you know, it's just coming from some mechanics. How do you get mechanics? Every day you practice them until the neurons in your brain connect, and then we talk about it on a deeper level. Right, so everything we're doing here, we're doing for the whole semester. Definitely not doing it sequentially. All right. So, definitions, square root, side of a square. Got to call it something. And the square root of 9, we don't say plus or minus 3, we just say 3. And there's a different reason for that. I think historically, probably people thought, you know, looked at square roots and said distances, and distances are always positive. Okay, so there's probably some evolution as to why this was stated, besides a more lengthy discussion about the vertical line test, which doesn't mean anything to you right now. But let's look at part of this quadratic model, just the ax squared plus bx equals 0. Well, I can write that as a product. That's the first rule of factoring. Now you've been hearing that for 4 or 5 straight days. So I take out what's common, ax plus b, which means I have a rectangle, ax plus b, and we want to get rid of the dimensions. What gets rid of the dimensions? 0 and minus b over a. Depending upon whether the a term is positive or negative, gives us either a positive, cup shape up, or if a is negative, cup shape down. But let's just say, for instance, that a 0 got you a 0 and a 100 got you a 0. Well, I bet you can tell me that x value now. I'm guessing you can tell me that x value. And if you said 50, you'd be right. Question is, can you tell me this x value? Well, it's the average, right? It's the average of 0 plus minus b over a divided by 2. Geez, I wonder what that gives me. Oh yeah, we've been practicing with it for 5 days. Minus b over 2a. Very important little formula for finding the x value of the minimum or maximum of a quadratic, which we'll talk about at the end of this video again. So that's one of the reasons you've been looking at that. There's also geometric reasons. Talk about that another time. All right, so what have we been practicing? Did I miss anything there? I don't think so. All right, so let's see. Push this back a little bit. Let's put this in here. Let's see if I can tip this so that it sees things pretty well. Yep, think we're good. Hope we're coming in under 45 minutes. I'm not doing this again. All right, so we have a cup shape up. You can see that over here. We've got 2 important values. I know that the y-intercept is on the left side of this cup, 0, 7. I hope you can see if x equals 0, how I get the number 7. And I want to know at what rate this is changing at 0. So I go ahead and I do my little 0 to 0.0001. And it turns out that the significant change is with this term. This one, 1, 2, 3, 4, 5, 6, 7. NASA would ignore it. It's 8 decimal places. So what is the change? I went down from 7 to 7 minus 0.0020. And if I do that division, I get minus 20. A rise over run of minus 20. Boom. At that instant. Must be a coincidence. No, it's no coincidence. So I'm on the decreasing side. And now all I have to do is find minus b over 2a. Minus b over 2a, 40 divided by 4. So I guess I'm using the same one over here, maybe not. But minus b, 20 divided by 4 is 5. All right, so we got 5. So if I put a 5 in some nice interesting patterns, I hope you've seen in class, you get 50 minus 100 plus 7. No accident here. No 2 to 1 opposite accident there. So minus 50 plus 7 is minus 43. So therefore, I now know, using my thought process, I now know that 5 gets me minus 53. All right, which means I already have my roots. 5 plus or minus the square root of 43 over 2. That must be something easy to do there if I can just do a random problem and tell you what the roots are. Yeah, say about 3 weeks. Most of you will be able to do that about as quickly as I can if we do it every day. That would be useful. All righty. Something else I wanted to say there? I think not. So let's look at this situation here. We're about 10 minutes away from being done with this. So cup shape up 372. And what are the roots? The roots are when this calculation hits a height of 0, and I don't think it does. So mathematicians for many centuries said no real solution until someone decided to give it a solution because someone had a marker in their hand. I think it was Gauss, I'm not sure. So the real issue here is, and I think you can see it over here, how do you get minus 1 for an area? And 1 times 1 doesn't do it. Negative 1 times negative 1 doesn't do it. So you go back to standard definition. You know, what is that dimension? It's the square root of negative 1. And the square root of negative 1 times the square root of negative 1 is by definition what's inside times what's inside. I didn't want to say it that way. I want to look at it this way. The inverse of those operations gives you what's inside. All right, so hopefully that has a little bit of meaning. Let me get my eraser here. Hoping this marker lasts for another 5 minutes. All right, and so this leads us into a topic. Mathematicians don't like writing this many symbols. So to express this concept, they use the letter I. So we have I times I, which shows up on your SATs a lot. I squared equals negative 1 by definition. And what does a negative sign do? Well, if I'm walking north, put a negative sign, I change directions and walk south. So what are the answers to this? Well, let's look at the answers to something that does work, a height of 14. Okay, that's bigger than 7, so that has answers, right? Because I think I got to go up 7 units to hit 14, and I think I got to go down 7 units to hit 0. So what could I do with this? Well, I certainly don't want to write it in that form. Not right now. I want to write it in 2x minus 3 squared plus 7 form. And we're going to set that equal to 14. So what do we have? 7 units from 14 makes that 7. Dividing by 2. Adding 3. Well, I got to do the plus minus square root. And then I got to add 3. Okay. So what have we really done? From 3, we move to the right. Root 7 over 2 units. Why? Because I got to square that, but I'm squaring something that's being doubled. So I got to start with half of it. In other words, all of these numbers, 3 plus minus the square root of 7/2, are written here. Right, so mechanically, to learn how to do this just takes a little bit of effort. You know, what goes where? The students who do that usually show up as the first ones getting it right on the board in the workshop. And I keep my eye open for that. It tells me something, tells me a lot. It tells me how I'm grading you. All right, so then the issue is, well, what happens if I made this thing go in the other direction? Well, I really have the same numerics, but I'm just imagining it's heading in the other direction. So let's set this thing to 0 and see how it changes. Well, that becomes a negative, right? And this becomes a negative. That becomes a negative. And what we do with the square root of negative 7/2 is we don't write it that way. We write it as the square root of 7/2 I. And that I represents that what we're thinking about the calculation going in the other direction. And what would the x values be? Now, I'm going to talk about this in much greater length during the course of the semester, explaining this, right? But can't have the discussion until it starts. And so this is simply the start of the discussion, and nobody's telling you, you have to understand what I'm doing immediately. In fact, I doubt you can, but got to start the discussion. So what are some of the just mechanics that we do? Almost done here. Hopefully 4 more minutes, we're done. Well, you know, we do binomial squaring with I. And I'm hoping you can see 25 plus 30i plus 9i squared pretty easily. All right, and hopefully you can see that. And what did we say I squared was? I squared was -1, so that's plus 9 times -1. And so we get 16 plus 30i. And I'm telling you right now, that calculation everybody can do by the end of the semester and do well. So if you're feeling panicked, stop. That's not going to be hard for you with 3 or 4 days of practice. Most of you will have it down. Some might take a little longer, but it's something I see everybody able to do, unless somebody's not looking at the problem at all. 7/4 minus 5i. Well, you know, there's a big difference between I cut in half and 2 divided by I. I can get a feel for that. I don't even know what that is. So we don't like, mathematicians don't like I in the denominator. So we move it. How do we move it? Well, we got to get I squared. And we also got to get rid of the middle term. So it's called conjugation. And the conjugate of this is 4 plus 5i. And this is 4 plus 5i. And if we multiply that out, we get 28 plus 35i over 16 plus 20i minus 20i minus 25i squared. And we can see that these cancel in the middle, and the conjugate will always make that happen. And what is I squared going to do? It's going to change the sign of the coefficient. So that's going to become a plus 25. Right? It's -1 times -25. So you change the sign of the coefficient, you add it to 16, and you get 41. Again, people have good success with this. It just takes a series of days of practice. So allow yourself that time. Don't panic. All right, what's next? Well, simplifying something like 5i to the 23. And again, what's the key? I squared. So this could be written as I squared. How many times do I have to do that to get up to 23? 11 gets me close. That gets me 22. And if I tack on another times I, looks like I'm there. And there's another way of saying I squared that's easier than saying I squared. And that's -1. And if we do that 11 times, -1 times -1 times -1, you start doing this and you'll see a pattern. Right? When I do it twice, it's positive. When I do it 3 times, it's negative. When I do it 4 times, it's positive. When I do it 5 times, it's negative. All right, so odd gets me a negative, and this is odd. So that's the same. Oh, I got to tuck in the times I here. So I got to do 5 times -1 times I, and that's equal to -5i. And most kids can do that without putting pencil to paper after a couple of weeks of practice. But you got to start it somewhere. All right, so that's just some mechanical stuff. Now let's get into the meat of it. What are we using this for? Well, we're studying the real world with mathematics. We're studying physics. We're studying relationships out there. And there's all kinds. There's quadratic, there's exponential. When was the last exponential thing that was really in front of us? COVID. You know, every 5 days, the number of people getting sick was doubled. That wasn't good. It was okay when it was, just a couple of folks out on the West Coast. But pretty soon, it spread to Europe, and then it came to New York, and it was everywhere, right? And so people were talking about flattening the curve, so things weren't accelerating. Public health policies, all kinds of things. Well, let's just go to the quadratic here. So 2x squared minus 5x minus 12 equals 0. One of the skills that you're going to learn is, can you factor it? And that's why we're practicing this. All right, so that we get better at getting some quick answers. And so you got 1, 2, 3, 4, 6, and 12. And I want to get 5 in the middle. So let me find it. So it looks like it's a 4 here. That gets me 8. 8 and 3 can be combined, minus plus. That's what you try to learn how to do. All right, so you'll get plenty of practice that on a daily basis. But let's just do a quick quadratic where we study something. So let's say the marker at 0 seconds is, 40 inches high. 40 inches high. And I'm just going to throw it up. Boom. Okay, so I'm about 68 inches. So I went up to 68 inches, and it took 0.19 seconds to do that. All right, random numbers here. All right, so what do I now know? I now know that I'm measuring from the vertex. So I'm measuring from, let's use t for time. T minus 1.9 squared plus 68. And I'm throwing in a 0, so I'm getting 1.9, negative 1.9 squared. That's how it's changed. And I've gone down, right? I'm measuring from there, down 28 inches. All right. So I've got myself a quadratic. It's a messy quadratic. I don't know what it is right now. But what's it going to tell me? If I expanded that out, I'm going to have AT squared plus BT plus C. I could set that thing to 0 right now and solve it pretty easily. That would tell me when it hits the floor. Right? Might be important. I can tell that I'm going up at a certain instant at a rate. I can then find the initial force that I put on the marker. In other words, we're using the math to study things that have relationships. And over time, this thing did what? Went up. Must have stopped going up because it came back down. So somewhere in all of this is gravity. All right, so just a little entry discussion here into where math eventually goes and how we use it. All right, that's the end of that. And I think I came in under 45, maybe under 35, because I don't see the little icon that tells me I got 10 minutes left in the video. All right, so hopefully stimulated a little thought, and we'll continue working with these concepts. And all I want you to do is keep working with them, and full credit. Once you understand something, you get full credit in this class. So I don't grade you till, last 3 or 4 tests before midterm, last 3 or 4 tests before the final. And every test is a final, so that you're working with this stuff and you gain a working knowledge, not just a chapter 1, section 6 test on Friday. Right? Oh, I can memorize what's done in that chapter and just give it back to the instructor and then move on. That doesn't teach you to think mathematically. All right, so we're trying to teach you to think mathematically so that options are available to you when you get out of school, and you don't have to take those options. But if you have interest in being an engineer, an architect, a physicist, you might have the foundation to be able to do it. And the only way you're going to get that foundation is to get a conceptual understanding of what you're looking at. That takes time. All right, you're going to be given plenty of time in this class to think about everything. All right, so just keep thinking. All right, hope you take that advice. Bye-bye.